Welcome to the lecture on root locus technique. Today we will discuss about the definition of root locus and the importance of root locus in control engineering. So here root locus is a graphical representation of the closed loop poles as a system parameter is varied. It is a powerful method of analysis and design for stability and transient response. It can be used to describe qualitatively the performance of a system as various parameters are changed. For example, if we want to see the effect of varying gain, we can see it, and it gives also the graphical representation of a system's stability. So we can say that root locus is the representation of the paths of the closed loop poles as the gain is varied. So let's see here a system. So we have this system, and we represent it at kgs. We include one parameter, that is gain. We take it out specifically. Also this gain could be the part of gs, but here we write separately k because we want to see how varying the k we can see the change in the poles of the system. So here we have cs, and here is the feedback transfer function hs. So this is forward transfer function, and this is feedback transfer function. Now we want the equivalent closed loop transfer function of this system. So we know that the equivalent transfer function we can write here as rs cs, and this is k gs upon 1 plus k gs hs. So this formula we have already derived, and we call it Ts equal to k gs upon 1 plus k gs hs, and this is called equivalent closed loop transfer function, or simply closed loop transfer function. So this we can call equivalent closed loop transfer function, or closed loop transfer function we can call. So this Ts can be written as, so Ts is k gs by 1 plus k gs hs. Now here gs is a transfer function. It can have a numerator and denominator part. So we can write here gs equal to n gs by d gs. So here we are saying that this gs is numerator by denominator, so numerator of gs and denominator of gs. Similarly, hs can be written as numerator of hs and denominator of Hs. So we can write Ts as, so we put these here. So K into, now Gs we can write Ngs by dgs upon 1 plus k into n gs by dgs into n hs by dhs. So we can simplify this and we can write here k into n gs into, so here dgs will cancel out and dhs will go here. So dhs by dgs dhs plus k ngs into nhs. So we can see that the, so here we can write numerator of ts by denominator of ts. So we see that the numerator of ts, or we get zeros from here if we put this equal to 0. So nts equal to 0 will give the zeros of ts, and dts equal to 0 will give the poles of ts. So we see that nts, that is the zeros of ts, is function of the ngs and dhs, and so the zeros of ts consists the 0, because here is 0 of gs and poles of hs, while the poles of ts or equivalent transfer function comprise the poles of gs hs, zeros of gs hs, and also here is function of k. So we can see that the equivalent transfer function poles is function of k, as well as it is function of the poles of gs and hs and zeros of gs and hs. So if we want to find the poles of for ts, we have to solve this equation. So we have to solve this equation for some given value of k. So suppose if we want to see the effect of k for some values of k, what is the location of poles? Every time we have to solve this expression, that is dgs dhs plus k ngs and nhs equal to 0. So we have to solve this equation for some value of k. We can find the value of s, that is the poles of the equivalent transfer function. This, and then from once we obtain the values of poles, we can tell whether the system is, these poles are to the left half plane, right half plane. Okay, so we can say whether system is stable or not, or if we know the location of poles, we can also tell about the transient response of the system. But this process is quite tedious and lengthy, and every time for any value of k we have to do this process. So here we can use the technique of root locus, because root locus is a graphical representation of the closed loop poles when some parameter is varied, like k is varied. It will show where these poles are for the values of k are varied, and we don't need to solve for each k, but the locus will tell whether these poles are going to the right half plane or not, so the system is stable or not. So root locus is the representation of the paths of the closed loop poles as the gains is varied. Here this 1 plus k gs hs equal to 0 will give us the poles, that is closed loop transfer function, poles of closed loop transfer function. So it means that kgs hs equal to -1. So for any value of k, if this relation is satisfied, that pole S is the pole of this closed loop transfer function. And because root locus is the locus of the closed loop poles, this means that pole will be on the root locus for some value of k. So if we represent this in polar form, so this we can write as magnitude and angle. So magnitude is 1 and angle is minus, so 180 degree odd multiple. So 2k plus 1, 180 degree. So means here we can say that mod k gs hs equal to 1. So this is 1 and angle is 2k plus 1, 180 degree. So mod k gs hs equal to 1 and angle k gs hs equal to 2k plus 1, 180 degree, where k equal to 0, 1, 2, plus minus 1, plus minus 2 and so on. So here this is polar form. So the root locus, a pole is on the root locus, it must satisfy these two conditions. And here GSHS is called the open loop transfer function. Open loop transfer function. So we should understand the difference between this open loop transfer function and closed loop transfer function or equivalent. So this TS is equivalent closed loop transfer function, but GSHS is called the open loop transfer function. And so we can find the gain for which if there is some pole on the root locus, we will find the gain for which this is on the root locus. So these are the some properties of the root locus. Now let's take one example, that here So this is RS plus minus ESCS. So here your GS is equal to K. So HS is 1 because here is unity feedback. So HS equal to 1. So here K GS HS equal to K into S plus 3 S plus 4 upon S plus 1 and S plus 2. Now let's represent the poles of the open loop transfer function GSHS on the S plane. So this is sigma j omega. Now the zeros minus 3 and minus 4, the zeros. So here is one zero is at minus 3, other is at minus 4, and poles are at minus 1 and minus 2. So this is pole minus 1 and minus 2. So these are the open loop transfer functions, poles and zeros, that is of GSHS. So we plot here. Now if we assume that there is some pole S on the root locus, or it is a closed loop pole of closed loop transfer function Ts, then it must satisfy these two conditions. So let's say that here is one point, this point, that is minus 2 plus J3 is on the root locus, or that is a closed loop pole. So here we know that here K equal to 1 by mod GSHS. So if here is a pole, that is here we have some S, so and this we can write as so this is a multiplication of the zero length and multiplication of pole lengths for the number of zeros or poles, because here GSHS is we can represent as zeros upon poles. So poles will go in the numerator and 0 will remain here, and so the difference between this 0 and this pole is the magnitude, is the length. So that's why we take the length. So here if we say that this is L1, this is L2, this is L3 and this is L4. So pole length, these points, the length from the pole, that is L3, L4 by the zeros length L1 and L2. So if this is on the root locus or on the closed loop, or it is a closed loop pole, this condition must satisfy, and so we can get the length, the value of the gain. However, whether it is on the root locus or not, it must satisfy this condition also. So if we take the angle KGSHS, so let's say this is theta 1, this is theta 2, this is theta 3, this is theta 4. So the angle should be, so sum of angle of zeros minus sum of angle of poles. So here theta 1 plus theta 2 minus theta 3 plus theta 4. So it must also satisfy this angle condition, because here we have satisfied the we have calculated the just the length or magnitude. Here it must satisfy the angle condition. So if this pole is on the root locus, it must satisfy this as 2k plus 1 180 degree. So it must be odd multiple of 180 degree, then only this pole can be said to be on the root locus, or it can be a closed loop pole for the certain values of k. And when we calculate this angle, let us say this is angle theta for this pole. So angle theta equal to, we can calculate this angle. So theta 1 is equal to this length L3 by L1, so tan theta 1. So we can find the angle. Similarly, we can find theta 2, this upon L3. So we can find that sin theta 1 equal to L3 by L1, and then we can find sin theta 2 equal to L3 by L2, and so on. So we can find this theta 1, theta 2, theta 3 and theta 4, and when we find that this theta is coming minus 70.55 degrees. So if this angle is not odd multiple, either it should be 180 or 3 times 180 or 5 times, so on. So this point is not on the root locus, or it is not a closed loop pole. However, if we take another point, that is minus 2 plus j 1 by root 2, for this point we get this theta equal to 180 degree, and so this point is on the root locus, and for this we can calculate the gain k using this method, and so we will get k equal to 0.33. So thus we understand that the root locus must satisfy these two conditions. If a point is on the root locus, it must satisfy these two conditions. So let's take another example. So here we take one example, that is so we can see here in this figure that we have an equivalent closed loop transfer function for some system, and we are getting this. Now as we define the root locus, that root locus is a graphical representation when the some parameter is changing, how the closed loop poles are going to change, or what path they follow, that is called the root locus. So here we can see that when we are varying the k, so k is 0, we put k, so this is the s square plus 10s plus k, So this s square plus 10s plus k equal to 0 will give you the poles S, the closed loop poles. So if k equal to 0, so here we will get s square plus 10s equal to 0. So s plus 10 equal to 0. So this means s equal to 0 and minus 10. So we will get the two poles here, pole 1 and pole 2. So pole 1 is minus 10, pole 2 is 0. Similarly, if we put k equal to 5 here, we put k equal to 5. So again we will get some pole here, that is we get minus 9.47 and minus 0.53. Then if we put k equal to 10, we get minus 8.87 and minus 1.13. Similarly, we are varying this k from 0 to with 5 increment, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. And we are going to get the two poles of the system for this varying k. And these poles we are plotting here on the s plane, that is sigma j omega axis is here, and we represent these poles. So first we represent for k equal to 0, we represent minus 10 and 0. So this is the pole 0 and minus 10 here. Now we are changing the k from 0, 5, 10, 15, 20, and these poles are changing. So minus 9.47, then minus 8.87 and so on, and this is moving. And from here also we can see that so our initial poles are here at 0 and then here at minus 10 at k equal to 0. Now when I am changing this, the poles are moving like this. So poles are changing when I am changing k's. Then at k equal to 25, we can see here at k equal to 25, we see that here the poles are distinct for k equal to 0 to 20. However, at k equal to 25, the poles are equal but real. So at k equal to 25, we are here at minus 5. The poles are, both poles are same, they are equal. And so these poles move here. Then we see that the poles are, when we 25 beyond at k equal to 30, the poles are the complex pair, minus 5 plus minus j 2.24 and so on. So the poles are being complex here. So the poles are going to here complex. And at k equal to 50, it is minus 5 plus j5. So here we have some pole here at minus 5 j5. So what we see? We see that for k equal to 0, we are starting with two real poles, real and distinct poles. At k equal to 25, the poles are real but equal, and beyond 25, the poles are complex. So we can see here that how this is called the root locus. These red lines are the root locus because they tell that how with the changing this parameter k, the poles are moving. And we can see that this tells many information. When the k is less than 25, we have real and distinct poles. So we know that we are in overdamped region, because this is second order system. When k equal to 25, we have equal poles, so we are in critically damped condition. And when we have k greater than 25, we are in underdamped system condition, underdamped. So the response of the second order system can be understood from this, that we are in these three different regions, and so the responses will be accordingly tangent response. Now we see that the poles never cross this axis, they are not going to the right half plane. So this system is always stable for any value of k, because this root locus is not crossing the j omega axis to go in the right hand side, because this is right half plane and this is left half plane. So it is always to the left half plane, so the system is always stable for, it is not unstable for any value of k, but it is stable. So we see that from the root locus we can see the tangent response, because we see the location of and movement of poles, so we can tell about tangent response and stability. So we discussed and defined the root locus, and in the next lecture we will start the how to sketch the root locus. So I stop here and I thank you for attending the lecture.